everyone, Mr. Boltri here bringing you video 2.8, in which we're going to be talking about how to shift our representation of motion. So to get us started with that, we're going to do an example. So let's say you were given a velocity versus time graph of an object that's moving and asked to make the position versus time graph. Well, we're going to have to take this velocity time graph of some object and then turn it into another representation of the same motion, another way to look at or think about the exact same thing. So we know that this means that the velocity of the object is negative 25 meters per second for the whole time, which if we were to translate it onto a position versus time graph, we would know means that the slope of the position versus time graph is negative 25. So now we have just shifted our representation from a velocity versus time graph to a position versus time graph. The important thing here is that these two graphs are showing the exact same motion in a different way. Just a little aside here, I just arbitrarily chose 1800 as an initial position because remember the velocity versus time graph doesn't give us any information about the initial position. So unless the problem tells you otherwise, you could have chosen 1800 or any of these other initial positions and they would all be equally correct. But let's just stick with the one example that I chose, which is, so it starts at this initial position and then moves with a slope of negative 25 meters per second. And it does that for the same amount of time, 50 seconds, because remember, this is showing the same motion. So why would we put in the effort to shift our representation like that? Why not just stick with the velocity versus time graph? Velocity versus time graphs are great. Why go ahead and make a position versus time graph? So you'll notice that on a position versus time graph, it's easier to see the position at any moment. If I were to ask you, what is the position at 20 seconds, you could very easily see that it looks like it's 1,150. Whereas on the velocity versus time graph, there's no easy way to figure that out. But we're also still able to calculate the velocity. It just takes us a little bit more effort because then we have to do rise or run to find the slope. Whereas on the other hand, if we look at the velocity versus time graph, it's easy to see the velocity. If I said, what is the velocity at 30 seconds, we could easily see that it's negative 25 meters per second. And we're still able to calculate the displacement by doing the area between the velocity function and the horizontal axis. So different graphs allow us to see different things in different ways, which is the major benefit of shifting our representation. We might be able to notice different things by looking at the slope or the area or just reading the values off the vertical axis. And it makes sure that we don't get stuck in one way of looking at things. If we only ever look at position versus time graphs, then we're not going to have the flexibility to look at a problem in different ways, which is what you're going to have to do no matter what field that you go into in your future. So I know not all of you are going to be physicists in the future, but all of you are going to be stuck looking at some problems. They may be math problems or relationship problems or job problems. And the important thing is that we don't just get stuck looking at them in one way, that we're able to come at the problem from a couple different angles. So this unit is, we're learning about motion, but we're also learning about how to look at problems in different ways. So that's what we're going to do with the specific context of, since this is a physics class, we're going to do problems about looking at motion in a bunch of different ways. But just remember, this is applicable in a bunch of areas of your life as well. So what does it look like when we apply that mentality of looking at problems in different ways for motion? Well, we've already done velocity versus time graphs and position versus time graphs, and hopefully you're getting pretty good and comfortable at moving back and forth between those two things. So also, we might want to write the equations, and equations are really useful because they are a just very compact way to represent what we can see in a graph, and they allow us to make predictions. So that's a really good and different way of looking at a problem. Then I'm going to give you two more, which are motion maps, and I'm going to show you what those look like, but they should be very familiar based on the first activity that we did in this unit. And then sort of the old handy-dandy description of the motion. So you may look at a position versus time graph and be asked to make the description, or you may be given a description and asked to make, I don't know, the velocity versus time graph. So by the end of this unit, you should be comfortable moving back and forth between any of these five. You can be given one of them and asked to make another one of them. And you should be able to do any sort of combination of these five things. So to get you start building your comfort level with this, we're going to go through an example, starting with a position versus time graph. So here we have a position versus time graph, which is red and then blue. And we are going to start with what hopefully is most familiar to you. We're going to make it into a velocity versus time graph. So to find the velocity on the position versus time graph, I calculate the slope. And remember, I'm going to have to find the slope of the red section first and then the blue section second. So choose 2 points in this first 4 seconds and then 2 points in the second 4 seconds, because it wouldn't make very much sense to choose like this point and this point, because that would just give me some random slope that doesn't represent either of the two velocities. So when I do that, I get a velocity versus time graph that looks something like this. Seems to have a velocity of 5 meters per second for the first 4 seconds, and then -2 meters per second for the next 6 seconds, from 4 seconds to 10 seconds. So that is, we've changed the representations of motion once, and now we're going to do it 3 more times. Next, moving to writing the equation for these 2 sections. So I don't know if in your math class you've gotten to piecewise equations, where there's one equation for the line between 0 and 4 seconds, and then another equation between 4 and 6. But I know that's a topic that you're going to explore more in Algebra 2. And I don't really want to teach it to you right now. So we're just going to write the equation for the first 4 seconds of the line and just ignore kind of the blue part of the problem. So the equation for the first 4 seconds of this line, again, using y equals mx plus b, we're going to have p is our y equals m, which 5 is our slope, times x, t, since we're not graphing y and x, we're graphing p and t, plus the vertical intercept, which is 3. So this gives us p equals 5t plus 3, which is awesome because it represents the first 4 seconds of the motion, and allows us to make predictions and that sort of stuff. Then we can do the same thing over here with the velocity versus time graph. We can also do y equals mx plus b, except instead of position on the vertical axis, now we have velocity on the vertical axis. So it's going to be v equals the slope is 0 times t plus 5, which we know 0 times anything is just going to be 0. So if we wanted to, we could rewrite this as v equals 5, which makes sense because for the first 4 seconds, the velocity is just 5. So now we have an equation for the position, and we have an equation for the velocity. And what we're going to do next is, so we have now done 2, we've shifted our representation of motion twice. First from the position versus time graph to the velocity versus time graph, and then we wrote the equations for both of those graphs. But in a problem on a quiz or a test, you might be given the position versus time equation and asked to make, I don't know, the velocity versus time graph. That would be kind of crazy. But with practice, you're going to be able to do it. Next, we're just going to do the handy dandy description. So with the description, you want to try to be as descriptive as possible, and importantly, you want to talk about the motion of the object. You don't want to talk about the graph. So don't say that the graph has a positive slope. Say that the object is moving in the positive direction or to the right. Don't say that the graph values are below the x-axis. Say that if it's a velocity versus time graph, say that the object is moving to the left. So here's an example of a description of this motion. So an object begins with an initial position of 3 meters to the right of the origin. And then it moves to the right with a speed of 5 meters per second for a total of 4 seconds. At that point, it immediately turns around and moves in the negative direction, aka to the left. You can say either of those, they're both acceptable, with a smaller speed, 2 meters per second for a total of 6 seconds. Notice that in my description, I do not include stuff that talks about the slope, because we're talking about the object. The object doesn't have a slope, the object has a velocity. So use the vocabulary words that we've been talking about in the class, and talk about the actual movement of the object and not the graphs for the object. Because remember, we're trying to shift our representation, and we're not talking about the graph here, we're talking about the actual object itself and trying to describe, using words, the motion. And the last representation that I want to show you, which has different benefits from the other 4, is called a motion map. And when I show you a motion map, hopefully this looks pretty similar to something that you've seen before, specifically classwork 2.1, when we had Mr. Incredible trying to shoot the electromagnetic cannon. This is basically showing the motion. These little dots represent the position at a bunch of different times. So down here, you can see the position, and this little dot, you'll notice, is at 3 meters, which corresponds to, it's circled, which represents 0 seconds. So 0 seconds, the position is 3 meters, which corresponds to our position versus time graph. And then there's a little dot, let's imagine that it's a car and it's leaking oil, and it just drops a little oil dot right here. So at 1 second, the position is 8 meters, which also corresponds to our velocity versus our position versus time graph. 1 second, 8 meters. And then it goes on from there, 2 seconds, 3 seconds, 4 seconds, 5 seconds. And then you can see all the different positions at all the different times. So a motion map is really useful because it's another way to see the motion. And this helps us to remember that the object is moving to the right and then moving to the left. Because if we look at position versus time graphs all day, we might start to forget that we're actually thinking about an object that is moving in the horizontal direction, because the position versus time graph it looks like an object that's moving up and to the right and then down and to the right, which is not what's happening. This is an object moving to the right and then to the left. So the motion maps are really useful in keeping us grounded in what's actually happening with the motion. And in order to interpret motion maps, my biggest recommendation to you is going to be to go ahead and label every point 0 seconds, 1 second, 2 seconds, 3 seconds, and on from there, because that really helps you to sort of remember that each of these dots represent the position, 13 meters, at a clock reading, 2 seconds. So if you are able to move back and forth between these 5 representations of motion, not only are you going to be an expert at Quiz 2D, but in order to do that, you have to really understand everything from the unit, which is why we save this for last, because it's a really good way to put everything together. So in our next class, we are going to practice moving back and forth between these different representations of motion. Again, growing that part of your brain that is able to look at problems differently and not get stuck in one way of thinking about or looking at things. But for now, this is Mr. Boltri wrapping up video 2.8 on shifting representations, and go Bears.